Hello student, welcome to our web optics course. Today we have lecture number 38 where we are going to discuss about the grating spectra or the intensity distribution that we derive for n number of slits. So, we have lecture number 38 today and discuss about the grating spectra or the n number of slits. So, for one slit or the single slit, the intensity distribution was I, which is a function of theta, was I naught sine square beta divided by beta square. For two slits, we calculate that intensity distribution, which is a function of theta, is I naught sine square beta divided by beta square and cos a square alpha. That was for two slits, and for n number of slits, the intensity distribution that we derived is I function of theta will be I naught sine square beta divided by beta square, then sine square n alpha divided by sine square alpha. So, these three distribution we calculate rigorously starting from the first principle, and from that you can see that if I put n equal to 1, we get back from this expression, we get back to the first one. If I put n equal to 2, I can get back the expression for the second one, that is for 2 slits. So, for 3 slits, 4 slits, what should be the value you can put by just putting the value of n. Also, you should note that here alpha is k by 2a sin theta, that is the value of alpha, and beta is k by 2b sin theta. What is a and b? That we not need to define also. That comes from the geometry of the for single slit we have one slit width and that slit width is b, but for multiple slit we have another parameter, and that is the separation between the consecutive slits. So, the separation between the consecutive slits is defined by a. So, that is a, and the width of the individual slits is defined by b. So, that is the two parameter I defined from the beginning, and based on that we calculate the intensity distribution, which is shown here. Okay, so, this is the basic structure we have. So, what we like to find today, we concentrate on the n slit problem and concentrate on this term, that what is the condition to get a maxima and minima for this term, because diffraction condition we know, but the interference condition we have, this contribution is coming due to the interference. So, we try to find out what are the maxima and minima of this function. So, the first thing we calculate here is the condition of maxima. Of the function, let me write explicitly, the function sine square n alpha divided by sine square alpha. I want to find out the maxima of this function. Now, from here you can see that when alpha, if I put alpha tends to 0 here, then the numerator and denominator both vanishes. So, I need to do the limit in a different way. So, the limit, if I put alpha instead of 0, if I put p pi, p is an integer. So, any integer of pi if I put here, then the value of this quantity, the limit of this quantity rather, so sine n alpha, let us remove the square because I am trying to find out the limit for this quantity. It will be simply equivalent to, using the L'Hospital rule, derivative of these things multiplied by divided by derivative. So, it will be n of cos of n divided by cos of alpha. So, if I put p pi here, and if I want to find out what, then this value will be essentially equal to n, and n is a large number and that is the maximum value of that. So, alpha equal to p pi is a condition for the maxima of this function. If that is the case, then I can write it as, because alpha is k by 2 and this is a condition of maxima. So, alpha is a k by 2 a and sin theta. So, k is 2 pi divided by lambda. So, we have, simply by putting, we have a of sin theta is equal to p lambda. That is the condition when the value of the p can take 0, plus minus 1, plus minus 2, etc. So, this is the value of these angles, or this is, if I write a sin theta is equal to p lambda. So, this is the values at which this function should have a maxima. So, let us now find out what is the condition of minima then, because minima is also, so we want to track this function. So, condition of minima condition of minima of the function, which function? This sin n alpha divided by sin alpha. It is a square, but I want to find out what is the condition of minima for this function. So, note that when, it is interesting to note that when n alpha is equal to, so this function vanishes when n alpha is equal to some integer s pi, right, s pi, whereas s is some integer. Under that condition, what happened? Sign of n alpha will vanish, but there is a restriction over s. Why? Because as soon as the value of the s is equal to such that it is a multiplier, as soon as the value of I mean s is such that it is a multiplier of the n, then alpha should be some integer multiplier of pi, and then the denominator should have an issue. The denominator, the condition is 0. So, the condition of the minima is the sin theta, this will be 0, but for the value of that particular alpha, sin alpha should not be 0. That condition should be there. So, as soon as I put sin alpha not equal to 0, that means the value of the s should not contain 0 or n or 2n etc., because at this point the function goes to maximum, 3n and so on. Because at this value for these values of s, what we get is sin alpha will be 0. Okay, because as soon as I put s equal to 0, alpha will be 0, s equal to 1, alpha will be pi, s equal to 2n, then alpha equal to s equal to n, alpha equal to pi, s equal to 2n, alpha equal to 2 pi and so on, and sin alpha will going to vanish. So, this is the value that should not be there, and apart from this we will going to get the value of s such that the sin in alpha is 0. So, alpha is essentially plus minus of, because minus sign is also there, s divided by n pi, that is the condition, and alpha, that is the condition of minima rather. So, that condition tells us that k by 2a sin theta is equal to plus minus s by n pi, and we essentially get a sin theta is equal to plus minus of s by n lambda. That is the condition for minima. Now, how the function, so how the function will look like? Suppose n equal to 8, suppose n is 8, that I know. N is 8 means s should be 1, 2, 3, 4, 5, 6 and 7. It should not have the value 8, it should not the value 16, etc. So, that means at n equal to 8, that is if I have 8 slits, because n determine the number of slits, then we get a spectra like this. So, I have a peak at some value of n, and there should be a minima seven number of minima before two peaks. So, here we have one minimum 1, 2, 3, 4, 5, 6, 7, and then we have a maxima again. So, here we have a minima, that is 1, here we have a minima, that is 2, here we have a minima, that is 3, here we have a minima, that is 4, 5, 6, 7. Okay, it is for n equal to 8. So, n minus 1 number of minima will be there, n minus 1 minima will be there in the spectrum for two consecutive principal maxima. So, these are the principal maximas we have, and we are going to get. So, it depends on the number of, the number of slits. So, if the number of slits we know, then we can define that how many minima is there. So, and how many maxima in between these two minima? There are maximas also. So, there are 1 maxima, 2 maxima, 3 maxima, these are the secondary maxima, 4, 5 and 6. So, we have n minus 2 maxima here. We have n minus 2 maxima here, which is in between this. So, now this secondary maxima, that one can also find the condition like we get for double slit problem, that how to get the secondary maxima. So, condition, now we are going to find out the condition for secondary maxima. So, essentially what we try to find, that we have two principal maxima sitting here, and then we have suppose we have this. So, we try to find out what is the condition of this secondary maxima. These are the principal maxima and these are the secondary maxima, and there is a distribution over theta, and we try to find out what are the conditions to get these peaks, what is the value of the theta for which I am going to get these peaks. So, the condition is straightforward, that d alpha of I2 is equal to 0. What is I2 here? I2 is that function sine square n alpha divided by sine square alpha. I write this function as I2. I2 I already used, so you can use I instead of I2, you can use some different, but anyway that is the thing essentially. So, this derivative gives us simply 2 of sine of n alpha and then cos of n alpha multiplied by n minus 2 of sine square, oh, 1 sine square will be multiplied here, multiplied by sine square, denominator we have a sine square alpha, so sine square alpha, then 2 of sine square n alpha function, and the derivative is sine alpha cos alpha, whole divided by sine to the power 4 alpha is 0. So, essentially this quantity is 0. So, that means if I take few commons, like here we have sin n alpha cos sin n alpha cos n alpha multiplied by n. So, 2n, so 2 okay, let us first cancel out this 2 will cancel out, right. Then what else we cancel out, what else is there. So, sin 1 sin n alpha will cancel out with this, then cos n alpha is there, it will remain there, but this sin alpha 1 will cancel out to this sign. So, essentially we have n multiplied by cos n alpha multiplied by sin alpha, that is equal to, that is the condition we have, that is equal to sin alpha sin n alpha into cos of alpha. So, that means we have a condition that n of cot of n alpha is equal to cot of alpha, or n tan alpha is equal to tan of n alpha. That is the condition we have for. So, we need to solve this transcendental equation. It will be one can solve this graphically only. So, if somebody solve this graphically, then he or she can find out the value of the alpha for which one can find out the secondary maxima. And what is alpha? What essentially he get? Alpha is k by 2 a and sin theta. So, for if given a and wavelength, essentially he find the solution of this theta for which one can get the secondary this maxima. So, that is the condition for principal, that is the condition for the secondary maxima. So, what is the condition for principal maxima? That we supposed to calculate earlier, but anyway. So, let us find out the condition for principal maxima, that is rather important. So, condition of principal maximas. So, the function is, our function f is sin square n alpha and then sin alpha, and we sin square alpha, and we show that these become maximum condition of maxima arises when alpha is equal to p pi, where p is some integer. P can take the value of 0 plus minus 1 plus minus 2 plus minus 3 and so on. So, limit alpha tends to p pi that we calculate of this function f is essentially n square, where f is this function. So, the principal maxima, I write IPM is equal to I naught sine square beta divided by beta square, that was already there, this term was already there, multiplied by n square. And if I write this entire term as some intensity I1, so this is equivalent to I1 multiplied by n square. So, n square times increment of the intensity I1 will be there for principal maxima. So, we can also find out what is the ratio of the intensity of the secondary maxima and principal maxima, and that we can do. For secondary maxima we find n of cot of n alpha is equal to cot of alpha. That is the condition we have. So, that condition, we can make use of this condition to find out what is the ratio, and we will do that in this way. So, I can write n square, say cos square n alpha divided by cos square alpha is equal to sin square n alpha divided by sin square alpha. This condition I get with the condition of maxima, and that is n of tan alpha is equal to tan of n alpha, or n of cot n alpha is equal to cot alpha, both are same. So, tan I write sin by cos, tan n alpha I write sin n alpha divided by cos l alpha, and then I write this. These things again I can write like n square into cos I write 1 minus sin square n alpha, cos I write 1 minus sin square alpha. This side is sin square n alpha, right, sin square alpha, which is equivalent to n square sin square n alpha divided by n square sin square alpha. Just multiply n square both the side. Now, we know that if I have two ratio A by B is equal to C by D, then I can write this is equal to A plus C divided by B plus D. By doing so, one can have for this quantity, for secondary maxima, sin square n alpha divided by sin square alpha, and that I calculate under the condition of secondary maxima, this is equal to n square whole divided by 1 plus n square minus 1 sin square alpha. So, I secondary maxima, intensity of the secondary maxima is which is equal to I of I naught sin square beta divided by beta square, and this quantity sin square n alpha divided by sin square alpha, but this quantity we need to calculate under the condition of secondary maxima. So, this quantity we calculated here. So, this is equal to something called I1, and that sin square n alpha whole divided by sin square alpha secondary maxima. Now, I just replace these things so that I can have I secondary intensity of the secondary maxima is equal to intensity I1 multiplied by n square multiplied by 1 divided by 1 plus n square minus 1 sin square alpha. So, that I know this quantity is essentially the intensity of the principal maxima. So, we have a relationship between the intensity of the principal maxima, the ratio of the intensity of principal maxima and secondary maxima as this. So, intensity of the principal maxima we have I1 n square that we calculated, and intensity of the secondary maxima is I1 n square multiplied by 1 divided by 1 plus n square minus 1 and then sin square alpha. So, the ratio, if I find I secondary maxima divided by I principal maxima, this ratio will be 1 divided by 1 plus n square minus 1 sin square alpha. Now, that is the ratio of the two maximas, and based on the value of n and alpha one can find out what value. So, that means I essentially calculate that this is the principal maxima and these are the secondary maxima. There are many secondary maxima. So, the ratio of the intensity between the principal and secondary maxima, that is this is I PM, and for here this is I SM. So, I calculate the intensity of the principal and secondary maxima, and that comes out to be this. By putting the value of the n and others, one can find out what is the ratio. So, I like to stop here because today I do not have the time to go forward. In the next class, we discuss more about this grating spectra, and if time permits, we also discuss about the resolving power of this multiple slit system, which we in general is called grating. So, with that note, I like to conclude here. Thank you very much for your attention and see you in the next class.